So today we will be talking about the states of matter. And you probably all are aware of this, and I believe I may have mentioned this in the beginning, but we are going to go into significant more detail today. So the states of matter or the primary states of matter are a solid, a liquid, looks ugly, and a gas. So of these three states of matter, what do you guys think has the highest energy of these? Yep, the gas has the highest energy. So let's say delta E will increase from left to right. So the difference in all these different states of matter is how these elements or molecules are interacting with one another. So if we have 3 beakers, let's say this is a solid. Let's give it some depth. So we just have some solid cube in here. Now let's say we have a liquid. Let's go to blue. And finally, let's go to a gas. Now, with a gas, we're going to need to do something to our beaker. We are going to need to cover it with some sort of plate to prevent the gas from escaping, essentially. I should also note that not only does the energy increase, but the temperature also increases. So when we go from a solid to a liquid to a gas, we are raising the temperature. So we could say when we go to a solid to a liquid, we are melting. And when we go to a liquid to a gas, we are vaporizing. So this is known as vaporization. And this, I said it was, and what you usually use to describe it as is melting. What we use to describe it is fusion. So when we go from a solid to a liquid or a liquid to a gas, we call that fusion. And when we go from a solid to a liquid and a liquid to a solid, we call that fusion. And when we go from a liquid to a gas and a gas to a liquid, we call that vaporization. Now, there are a few other things that can be done here. We could go from a solid to a gas. And does anyone know what that is called? Yep, sublimation. And an example of sublimation, have any of you ever seen dry ice before or handled dry ice? So dry ice is really, really cool. Dry ice is, and by cool, I mean that both literally and figuratively. It's incredibly cold, and the idea of what dry ice is really neat. Dry ice is what you get when you take CO2 and you lower its temperature to the point where this gas turns into a solid. So right now, when you have dry ice, you have solid CO2. So when you set dry ice out and let it sit, instead of turning into a liquid, it actually turns into a gas. And the reason for this is because the pressure in the atmosphere is not great enough to actually force it into the liquid state. And we'll go over that in a little bit, but I just wanted to go over the general ideas of what's going on here, because what we will be mainly talking about today are what is known as intermolecular forces. Let's close this. All right, so intermolecular forces. I want to underline this word right here, inter. So we actually have two different words we can make that are similar. So inter and intra. Molecular. So, do any of you guys know what these two words mean? So pretty much everything that we have been talking about have been under or defined as intramolecular forces. So intramolecular means between the atoms. Or inside the molecule. And inter means between the molecules. So when we were talking about atoms and bonds and all of that was under the idea of intramolecular forces. We are now switching over to intermolecular forces, and this is the idea of the things that go on between the molecules and other molecules. So we need to take a step back, sort of think back to before this last section we were talking about, and remember when we were talking about molecular geometry. So remember the idea of polar and nonpolar? Polar. has a dipole. Doesn't. So, when we talk about intermolecular forces, we need to always be sure the molecules we are talking about are either polar or nonpolar. So, let me list these forces. So, we have ion, dipole, we have ion, induced dipole, we have dipole-dipole, we have dipole induced dipole, we have London dispersion forces, also known just as dispersion forces. And we have hydrogen bonding. So these are the primary intermolecular forces that occur between molecules in all states of matter. And what we will be talking about for the rest of today's lecture is we will be breaking down each of these, and we will be discussing what forces are present between different types of molecules and why they are present, and how those forces influence other aspects of the molecule and the behavior, essentially, of a substance. So what do I want to start with? Let us start with dipole-dipole. Now I want to actually state right here, special case dipole-dipole. So hydrogen bonding is a special case of a dipole-dipole interaction. So let's go over a dipole-dipole interaction just in general right now. And I know these D's look like J's, so let me fix that. So in a dipole-dipole interaction, the name of it somewhat is explaining exactly what it is. We are talking about an interaction between two polar molecules, essentially. So what is an example of a polar molecule? Could someone give me an example of a polar molecule? Let's do something besides water. Let's do HCl as one. All right, let's use HCl. Because water is going to be the special case. Water is a special case, and it presents something called hydrogen bonding. So HCl is a polar molecule. And we have a dipole in this direction. So when we have HCl, we have a bunch of these guys floating around in solution. So let me try to redraw this. So we are going to have a partial positive charge here and a partial negative charge here. Blow this up a little bit. Let's make the positive red. Let's make the negative blue. All right. So here we have our HCl molecule that has the electrons distributed like this. So what's going to happen is, actually, let me redo this a little bit. I don't like these partial positive charges inside here. Just kill them all together. All right, I like that better. So what's going to happen is we have a bunch of these guys floating around in our solution. And when that happens, they're going to essentially line themselves up like this. So they have some sort of interaction going on between them. This right here is our dipole-dipole interaction. So if you are asked a question specifically, what would be the intermolecular forces between HCl? It would be a dipole-dipole. And the reason it is a dipole-dipole is specifically because of this. Now I want to talk about hydrogen bonding next, because it is a special case. All right, so hydrogen bonding. So hydrogen bonding, I actually need to pull my notes up really quick. Just to confirm with you guys, a new notebook didn't pop up for you. You're still seeing the same notebook that says hydrogen bonding, special case, dipole-dipole? Awesome. this. I guess I lost my notes on this. All right, so I'm gonna make some new stuff. So hydrogen bonding is the special case of the dipole-dipole. And the special case exists for HF, O, H/O, let's see, and H/N. So these are all the cases which hydrogen bonding essentially can occur. We essentially need a bond from hydrogen with a fluorine, oxygen, or a nitrogen. And what's the reason for this? Well, the reason is because fluorine, oxygen, and nitrogen are all very electronegative. So very and what's going to happen is fluorine, oxygen, and nitrogen will pull the electrons from hydrogen it should only be one electron harder than any other combination. So what you're going to get is you're going to get a partial positive charge on this side that is much higher than the partial positive charge on any other dipole moment that you would get. Oh, that should be negative. So this is going to generate the strongest dipole moment that essentially can be generated. And as a result, things that connect to these things will stick very strongly. So let's look at H2O. So we have oxygen. Let's make this a little shorter, actually. And it's going to look something. There we go. Something like that. So let's color that in. What we're using? We're using blue for negative. So we're going to have a very strong negative region right here. As a result, we are going to have a very strong positive region right here. So let's put a partial positive, and partial negative right there. So here is an example of water with its OH bond, which is causing a dipole. And so let's take this. Let's move this a little right there. Let me shrink this a wee bit. I could put there. Go there. Go there. Now let's just delete this one. So the forces here are going to occur as such. Now, I want to note something at this point. What's going on here is essentially the reason why water has such a high boiling point. The reason why water requires so much energy to be pumped into it to bring it into the gas state. When we talk about these transitions up here, from solid to liquid to gas and vice versa, when we are going from a solid to a liquid and a liquid to a gas, what we are breaking are these bonds. These not bonds in the sense of bonds that we previously talked about, but these intermolecular bonds are being broken and rearranged. And therefore, the stronger these intermolecular bonds are, for instance, the more energy that the molecule is capable of absorbing before it raises its temperature or before it transitions into another phase. So the stronger these bonds are, the more energy essentially the substance is capable of absorbing before transitioning in temperature or phase. And this is the reason why water is so awesome. These bonds are so strong that water is able to take a huge amount of energy before transitioning. And we'll be talking about that probably this Thursday. But this is going to be more conceptual stuff today. But that is the reason behind all of that. And yeah, just keep that in mind. So today, just to reiterate, we're going to be talking about more conceptual stuff today, like this. And on Thursday, we're going to be talking about more mathematical stuff. So the math that goes behind this. So this is essentially what a hydrogen bond is essentially going to look at. So examples of other molecules. So obviously, if you see H2O, this is examples of a hydrogen bond, H2O with itself. NH3 with itself. Let's see, what else? We have F, hydrofluoric acid with itself. Hydrogen bonding is able to be done through H2O, but it's also things like, for instance, C2H5 OH. This is ethanol right here. So, for instance, we have carbon, 1, 2, 3, 4, 5. We are going to have this, essentially this electronegative region right here. Let me not even draw that. Let's show this partial negative, partial positive. And so we could have hydrogen bonding between other ethanol. This might get a little bit sloppy. I'm going to use this one. This is more let's see. Can I rotate this at all? Nope, that's not what I wanted to do. So there's going to be a hydrogen bonding effect right there, because there's going to be, let me actually rewrite this so it's not so difficult to see. This is going to be a partial positive, partial negative, partial positive, partial negative. And so hydrogen bonding. I want to also note that we don't need it to occur just between the same molecules. For instance, we could have hydrogen bonding between H2O and water. or H2O and ethanol rather. We'll put that there. Oxygen, hydrogen, and what's actually going to happen in this case is because water is actually so small, we're going to have a bunch of waters that are essentially just going to surround this thing. So we're just going to have a bunch of hydrogen bonds being formed all over the place on this molecule. So let's hydrogen bond. So whenever we have any molecule that has HF, HO, or HN, and they are in solution, we will say that they are capable of forming a hydrogen bond with each other or something else that also has an HO, HF, and HN. So you could sort of just think about as a very, very powerful magnet. And the negative pole will be here, the positive pole will be here. And we'll just put X there for whatever X equals F O N. So, are there any questions on this so far? I would also like to, not yet, not yet. We'll talk about this once I finish all these courses. So let's see, we did hydrogen and dipole. Let's do dipole induced dipole. So, question, do any of you guys know what induced means? So if you are to induce something, it's not a chemistry term, by the way. If you are to induce something on something, you are essentially forcing something on it. So for a dipole induced dipole, it means something that has a dipole forces a dipole on something that doesn't have a dipole. So we have two induced dipoles, or an ion-induced dipole and a dipole-induced dipole. So both of these things have the idea of a dipole being forced on something that, well, doesn't have a dipole. So let me see if I could think of an example. All right. So let's use water again, because water. Let's use water for our dipole molecules, because water is just awesome. It has a very nice dipole that's very, very strong, and so let's use that to our advantage. So a dipole and induced dipole would be something that was between, say, for instance, oxygen, O2. So H2O and O2 dipole induced dipole. So, question, is O2 a polar molecule? Does it have a dipole? Yep, water and xenon is actually used a lot. Xenon is, I wanted to use a molecule here, but xenon is usually the universal example of a dipole, induced dipole. For instance, you could have xenon. So if you guys refer to the periodic table really quickly, you'll see that xenon is a noble gas, and specifically it is a noble gas that is very, very large. It occurs very far to the right and mostly far to the bottom of the periodic table, so it's a big, big molecule. And because it's such a big, big molecule, xenon by itself, let's say we don't introduce the water molecule yet. It's the shape because I cannot draw a circle. Xenon is going to have a bunch of electrons essentially floating all around it. So by itself, xenon is going to have pretty much no dipole moment. So let's go to the right. And now let's add xenon in the presence of water. what has essentially happened is this electronegative end of the water molecule. Let me go back to white. Is we just did what's called an induced dipole. So what's happening is I hate it when it just doesn't allow me to switch pen for some reason. Yeah, it's just refusing to switch the pen for some reason. There we go, maybe. So what we did, oh man, I am really failing here, is we exposed a portion of the nucleus. Let me actually delete this. Of the xenon molecule to allow this dipole to occur. When we brought the water molecule really close to the xenon, what happened is the xenon was pushed in a way. The electrons in the cloud were pushed away, and that pushing away from the cloud of the electrons caused this separation of charges on the xenon molecule. I want to note that this special case with xenon, it won't occur with smaller molecules. Xenon essentially is doing this because xenon is so big. This is why xenon is used as an example so often. Xenon is such a large molecule. It has such a large electron cloud. This large electron cloud is very easy to essentially be pushed around and manipulated. Oh, someone just requested to join. One sec. Yep, O2 is nonpolar because they are equally electronegative. So the same idea with O2 happens. What's going on is we are pushing this electron cloud away. And thus we are generating a partial positive and a partial negative charge. Negative, partial positive, partial positive. So whenever you see a dipole that is being induced, it's because we have a pushing or we have a pulling of the electron cloud from an element that does have a dipole or does have some sort of electronegative or electropositive charge. That makes sense? So that is an example of a dipole, induced dipole. So if you have questions that, and pretty much have an example that has a molecule that is polar with a molecule that is not polar, that will most likely be a dipole, induced dipole. Right, so the next example. Ion dipole. Now, do any of you guys remember what an ion is? Yep. So anything that has a negative or positive charge. So an ion positively or negatively charged species. So cation or anion. So this is a very, very simple type of intermolecular force to explain. It's very, very straightforward. It, based on the previous one, it's much more simplistic to understand. So pretty much we have a polar molecule. Let's just keep using water because water is just so awesome. There's something that is very interesting that we're building up from all this, and it will describe to you why certain things will dissolve in certain things and why some things won't dissolve, why some things are able to be mixed with some things and why some things aren't. The entire idea of what we're talking about right here is pretty much that. So it's negative, positive, positive, and let's use something like sodium with its positive charge. So we have a positively charged compound matched with our negatively charged or partially negatively charged end of the oxygen. I want to state that let's actually make this example H2O with NaCl, and we will see that the Cl's will actually bond to the positive ends of the hydrogen. This is why when we take salt, sodium chloride, and add it to water, it dissolves so easily. The water is able to break apart the sodium chloride with great ease and essentially distribute its charges very nicely throughout it. This is the main reason why so many salts actually are soluble in water, and it's because of that charge. Let me think. Do I have another example of this one? Let's do, for instance, let's use magnesium. We have water. Put our partial positives, partial negatives. And so we put the magnesiums right here. And I should state that this is actually going to be a very strong bond because the magnesium has such a powerful charge. It's really going to grip. And again, we have the chlorines here. So whenever you see a molecule that has a dipole moment matched with a molecule that is an ion or an ionic compound like NaCl, MgCl, pretty much any ionic compound, we will almost always form what is known as a ion dipole. Any questions on that? All right, no questions. Lastly, or not lastly, let's talk about ion-induced dipole. It might be lastly. Did I hit them all? I think I talked about them all so far. And an ion dipole, 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 dipole-induced dipole. Oh, dispersion forces. So, ion-induced dipole, exactly the same as dipole-induced dipole. So, let's say we have a molecule like, again, sodium chloride. And we're going to add it to O2. And exactly the same as our previous example. We will see that the sodium you will have a positive charge here and a negative charge here, which means we have to have a partial positive charge here, and we will have a partial negative charge here. As such. So what happened is the sodium and the chloride essentially induced a dipole on this O2. And it did so by essentially pulling and pushing the electron cloud. The negatively charged chlorine would rather be attached to the nucleus of the oxygen rather than by its electron cloud. So it pushed it away. while the sodium wants all those electrons because it has a positive charge. It gripped and yanked it towards them. And so as a result, here is an example of our ion-induced dipole interaction. Any specific questions on this? This might be the only example I give for this one. No questions? We're all good so far? So the last thing we're going to talk about today is dispersion forces. And dispersion forces are the simplest, and they are also the weakest of all the forces. Amber, I can't tell if you're talking or not. I'm not sure. Are you talking? Did anyone hear someone talk? I saw Amber's photo pulsating, but I'm not sure. All right. Well, let's continue that. Oh, no worries. All right, so dispersion forces. Dispersion forces are also known as London dispersion forces, and they take place between two or more nonpolar molecules. So whenever you see something that is nonpolar, that will be an example of dispersion forces. So what's going to happen? We are going to have, I'm definitely going to use the circle tool. Let's do this again. It's the typical shapes that are. So let's put red nucleus in the center with some electrons floating around. And as we move them closer together, it's not going to let me grab stuff. we are going to see this sort of happening. This is incredibly exaggerated, by the way. I want you guys to know this is not any way depicting of what actually happens. This takes place to a much smaller extent, but I just want you guys to sort of see the idea of what's going on. So this is the force right here. So dispersion forces, examples would be things such as CH4, C2, H6, C3, H6, H8. Pretty much things that are hydrocarbon chains, things that have pretty much no oxygens on there, no nitrogens, nothing polar. We are going to see that in things like, for instance, oils, waxes. That's a good thing. That's about it. So anytime when you see a nonpolar molecule, the forces that take place between itself and something else, these are known as dispersion forces. Any questions on this specifically? So this is where I technically want to end, but let me try to give you guys some examples just so you're not completely cut off. So I2 with I2. Let's say NH3 with CH4. Let's say HF with H2O. Let's say H4 with C2H6. Let me think. What else? NaCl with. Yep, that is the exact reason why oil and water will not mix with each other, because one is polar and one is non-polar. This is the exact reason why everything either mixes or doesn't mix with one another. If you are able to determine the polarity of the molecule, you could determine if that molecule can mix with something or it will not. Let's say with H2O. I think of one more. CH3Cl with So, can you guys tell me what type of dipole or intermolecular force is present for each of these? Start with that first one, I2 with I2. What do you guys think? Any ideas? Yep, dispersion. How about NH3 with CH4? So NH3 has a dipole, but does CH4 have a dipole? What type of molecule is CH4? Polar or nonpolar? So polar and nonpolar. So this will have a dipole. So nope, no ion dipole because we don't have an ion here. It is dipole induced dipole. Whenever we have a polar compound with a nonpolar compound, that will mean that the dipole has to be induced by the polar compound. That's why it is dipole-induced dipole. So whenever you see polar, nonpolar, it means dipole-induced dipole. So what about HF and H2O? Yep, hydrogen bonding. Make sure not to mistake hydrogen bonding with dipole-dipole. They're the same, but hydrogen bonding is a special case. So how about CH4 and C2H6? Well, it's hydrogen bonding specifically because we have to remember the special case for hydrogen bonding. Hydrogen bonding needs to have HF, HO, or HN connected to another HF, HO, or HN. So you need to have one of these three things essentially participating in intermolecular forces with another one of these things. These three molecules or three combinations of elements right here form a very powerful negative bond, which I sort of depicted with this magnet. And so it created a magnet that's much, much stronger than any other magnet that would be created through any other combination of elements. That's why the dipole that is present between HF, HO, and HN are much stronger than the dipole that is present in any other molecule. That's why it has a special case called hydrogen bonding. And yes, it pretty much always has to have hydrogen. But just because it has hydrogen does not mean it's hydrogen bonding. That hydrogen has to have an F, O, or N connected to it. So this CH4. So you say CH4 with C2H6 is dipole-dipole? Is CH4 polar or non-polar? So non-polar. And what about C2H6? So nope, this isn't induced dipole either. So is C2H6 polar or non-polar? I gave you guys examples right here. So C2H6 is indeed non-polar, but if you wanted to draw it out, it would look like this. Yep, dispersion. Whenever you have two nonpolars, it's going to be dispersion. And just to reiterate again, it is sometimes called London dispersion. How about NaCl and H2O? So ion dipole is correct. And how about CH3, Cl, HCl? Yep. If you have two dipoles, it is always going to be dipole-dipole. So two polar molecules means dipole-dipole. So that's how we do that. So that is pretty much all I want to talk about today. Are there any questions on any of these things? Okay, so if there are no questions, let me stop this recording. Stop recording.